Have you ever wondered how PCB thickness influences reliability? In this video, we'll explore the critical role of PCB thickness in preventing warpage and ensuring interconnect reliability. PCB thickness ranges from 0.8 mm to 2.2 mm, proper optimization limits, warpage to 0.75%. This limit is vital for interconnect reliability during extreme thermal cycling. Firstly, let's define PCB thickness. It's a key design factor affecting mechanical, thermal, and electrical reliability. It's a misconception to view thickness just as a physical dimension. The z-axis dimension impacts stress distribution, thermal loads, and component interactions. Now, what are the failure mechanisms? Three main scenarios include warpage, via failure, and thermal cycling degradation. Choosing the right thickness helps engineers identify and avoid these issues. Next, let's analyze mechanical reliability. Thickness directly affects stiffness and bending resistance. Reducing thickness from 1.6 mm to 0.8 mm decreases structural rigidity, increasing the risk of bowing during assembly. Warpage isn't just about thickness. Other factors like coefficient of thermal expansion, CTE, mismatch, and uneven copper distribution also play significant roles. Excessive warpage can occur during assembly or long-term use, so manufacturers enforce limits, capping deformation at 0.75%. In terms of dynamic loading, thick and thin boards behave differently under vibration. The z-axis dimensions influence displacement during stress. Therefore, it's essential to consider thickness alongside fastening methods to prevent failure at solder joints. Thermal cycling introduces additional stresses, particularly around plated through holes, PTH. CTE mismatches create concentrated stresses, leading to potential failures in complex designs. When evaluating copper plating, ensure adequate thickness and quality. Thin plating increases failure rates after thermal cycling. Protective wrap plating is necessary to avoid failures due to z-axis expansion. Under thermal cycling loads, board thickness affects heat dissipation and stress distribution. Thicker boards hold more thermal mass, impacting the stress manifesting in PTHs and interconnects. Let's compare thin and thick boards. Thin boards save space and cost but are sensitive to warpage and thermal stress. On the other hand, thicker boards provide rigidity, but may shorten solder joint fatigue life. Industry applications vary in thickness requirements. Consumer electronics often use 0.8 mm to 1.2 mm, while automotive systems require thicker boards for vibration resistance. High-power boards demand more thermal mass, typically exceeding 2.4 mm. Testing standards like IPC 6-12 evaluate board reliability through rigorous protocols. They measure total cycles to failure and crack lengths, ensuring compliance with dimensional tolerances. To avoid failures, hardware teams should follow thickness-sensitive guidelines. Advanced simulation methods, like finite element analysis, FEA, help predict thermal impacts and mechanical stress before manufacturing. Future research needs to focus on systematic data gaps in PCB reliability studies. Collaborative data sharing will enhance predictive models. Machine learning may be key to optimizing board thickness and complex via designs. In summary, understanding PCB thickness is crucial for reliability. It influences warpage, via performance, and overall longevity under thermal stress. If you found this information helpful, consider subscribing for more insights into PCB design and reliability.